part, this is our last chapter. There is one section of chapter 8 which we'll cover, which is going to rock your world, but that's like one day of work. Chapter 7, however, is rather lengthy, and it can be a little scary. So we're going to go slow, and hopefully all the puzzles will fall into place. Now, the one good thing about chapter 7 is it's very algorithmic. Do you know what I mean by that?
It's a pattern.
I'm sorry?
It's a pattern.
Alex?
Memorization.
No. You want to look it up? Oh, I thought you were grabbing your iPad to look up
I'm
algorithms.
just putting it away.
Okay. It means step-by-step process. Okay. So we're going to start today by talking about finding area of some figures. Then we're going to take some figures and we're going to revolve them around axes. So think about you have a square sitting with one corner of the square at the origin. Are you visualizing this? Spin that square around the x-axis. What do you get?
A line.
Nope.
Another square.
Nope. Nope.
Another square.
Nope.
So that says 2 squares.
No.
A rectangle.
No.
Triangle.
No.
The same square?
Let me say it again.
Circle.
You have a square sitting with its lower left-hand corner on the origin. You with me?
Yeah.
One side is the y-axis, one side is the x-axis. You spin that figure around the x-axis. What do you end up with?
Negative square.
Dennis, was that you?
It's a cylinder.
You get a cylinder, correct. Take a semicircle. Let's say the top half of a circle. Sitting on the x-axis, symmetric about the y-axis. You spin that around the x-axis. What do you get?
A dome. A sphere.
A sphere, right. We're going to be calculating the volume of those types of figures. Okay. Let's say you've got a 45, 45, 90 triangle sitting on one of its legs on the x-axis. You spin that around the x-axis. What do you get?
Square.
Nope. Somebody said it. Cone. Dennis, are you like a 3D savant here? If it was common sense, 26 people would be yelling it out.
But it's like
Someone get Dennis.
but it's like a triangle and then you like circle and it's like
I don't know, it's kind of funny. If I take that and I spin it around that, you get a cone. Okay. This bottom is going to become a circle.
Oh, it's 3D.
There you go. Sam just got it. Oh, it's 3D. Yes, you are correct. Okay, so we good? You got the idea. It would be nice if the entire chapter was just take this rectangle and spin it, take this triangle and spin it, take this semicircle and spin it, but it's not going to be. We're going to look at things like, let's take this figure. We'll start here, we'll go, and then there. And what happens when I spin that thing around the x-axis? Yeah, good. That's the best way to sum it up. Something crazy. Not only are you going to have to visualize that, but you're going to have to calculate the volume of that thing. Oh yeah, it's going to happen. And it's going to be easy.
so the cylinder.
Well, it's kind of a cylinder that somebody went inside and pushed out part of it.
It's
Like a ShamWow.
If you like
Yeah.
stretch it up a little bit.
Right, just like that. Good job.
So once you go next to us, you can get-
But before we get to that, we got to do some other stuff. So let's do something a little bit easier today. We're just going to do some area. And I'm going to ask you to figure this out. So we're going to find an area of a region. So we got to get some terminology under control. We've used some of the terminology already. Things like bounded by, that kind of business. We're going to do some top and bottom changing. That doesn't make any sense now, but it will later. And then we're going to go back to the idea of a integral being an accumulator, adding things up. So we've used the integral as an accumulator of area. Today we're going to continue doing the accumulation, I should say, of area. But eventually we're going to shift to the accumulation of volume. That'll be fun. And you should all be able to make good scrambled eggs, yes? Milk or water?
Milk.
Milk, good.
Wait,
There's no
scrambled
flavor
eggs.
otherwise. Yeah, one.
Wait, what?
When you
Yeah.
like mix the
What?
eggs, you add a little.
Don't you just like
milk.
go like this?
Okay, time out. Time out. What do you say?
Wait, so when you make scrambled eggs, don't you just like crack the egg and then you just like break it up? You don't have to
Wait, so
add
add
stuff.
water either.
Definitely add milk.
No, you know what that
The argument is, do you add milk to the eggs or do you add
You
water
don't
to
add
the eggs?
anything.
Then that's not scrambled
Why-
eggs. That's
Yes.
no, that's
What is it?
Eggs that are scrambled.
mush. Just an egg. I mean, it's just,
Unfluffy scrambled eggs.
one school of thought says that if you add water, you get fluffier eggs. Other school of thought says when you add milk, the fat bonds with the egg better, and you get a better tasting egg. You gotta add something. You did. Really? You just whip the snot out of an egg and then throw it in a pan and whatever happens happens?
Yeah.
That's what I do.
Really? Have you ever had like good scrambled eggs?
With some garlic salt?
I don't like scrambled eggs, but that's how I see people make them. They don't add stuff.
Then they're children.
Like when you're peering in people's windows and stuff on Sunday mornings when you creep around the neighborhood? You don't eat scrambled eggs at home? Okay. Scrambled eggs, yeah. Not scrambled eggs. Okay. I got nothing else to say. All right, so here's our picture. We've got a one function, the red one. We've got another function, which is the blue one. So the one function you could imagine being maybe a sine graph or something trigonometric, especially since the axis is labeled in pi values. And then you've got this blue one, which could be a parabola, could be another trig function. It doesn't matter. And then I take some vertical lines. Okay, this line is at 1, this line's at 2. And we generate a region here. And the terminology you'll hear is things like the region bounded by. Okay, so that region is bounded by the two functions f of x and g of x, and the lines x equals 1 and x equals 2. In order to do the stuff that we're going to do today, you have to have a finite region. Okay, you just can't go on to infinity, because you're not going to be asked to find the area of an infinite region. How do I find the area of that green region? And again, assuming you know the equation of the red function, the equation of the blue function. Rick?
Area under the curve of the red minus area of the curve under the blue.
Why?
Because if you do the red, then it gets everything, but then after you subtract the blue, then it takes away the space from the bottom.
Let's give it up to Mary. Well done. Blah, 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 blah. Terminology you already did. Blah, 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 blah. So as she said, the area under the curve of the red function is that whole reddish, burnt red shape, whatever you want to call it, represented by this. Because again, remember, an integral is the area under the curve. So from A to B, A and B are vertical lines that we're using. And then f of x is just the function. Then the blue part comes about from taking the integral from A to B of g of x. And if you subtract those two puppies, you end up with that green region. Okay. Well done. Which gives you that. Question in the back.
Will the other horizontal line always be y equals 0?
What other horizontal line?
Well, is it always going to be bounded by the y-axis?
It's not bounded by the y-axis.
Or the x-axis?
It's not bounded by the x-axis. This green region is bounded by f of x, g of x, and those two vertical
I'm
lines.
saying g of x. Will all for g of x, will all those just go down to the x-axis? Or will they give us like
How is this defined?
the area under the curve until the x-axis? Oh,
Okay. There's the fancy eduspeak, or the calcu-speak, if you will. Two functions, f and g, they're continuous. That's important. That means we don't have any gaps or anything. On the interval from a to b, including a and b. This is important. G of x has to be less than f. That's supposed to be an f. I don't know what happened to the cross piece of that. Has to be less than f of x. And this we already know because this is what Mary told us and we believe her because she has an honest face. The thing you want to get out of that is this. Top minus bottom will become a huge buzz phrase in this chapter. Pregunta.
You can't just subtract f minus g and then do the integral of that, can you?
You can, yeah.
Oh, you can. Got it.
Because remember, you could do f minus g and then do the integral, or you could do the integral of f, do the integral of g and subtract the two. Because you split it up into two different ones. It's entirely up to you. Okay. There's another one, but this will get us started for now. Top minus bottom. Always. No exceptions. And it's so important it changes colors. Okay, accumulator we talked about already, adding things up. Okay, now what are we going to add up? This is another crucial thing that's going to get you far in this chapter. We're going to use something called a representative rectangle. So we're going to take any region that we're dealing with, whether it's an area, whether it's a volume, whatever it is, and we're going to break it into a little skinny rectangle. This is a little confusing to see, but we've got the red curve here, f of x, we've got the blue curve here, g of x, and then I want to find the area of this black crossed out area. I use this thing, which again is a little hard to see, so let me do that. I use that thing to stand for what I call a representative rectangle. It represents one little sliver of area. And notice that the height of that thing is f of w minus g of w. Because again, top minus bottom. What's on top? F of x. What's on the bottom? G of x. Okay, you with me so far? Now what we want to do, because this is calculus, is we want this rectangle to be really, really skinny. And the theory is this. If I draw this representative rectangle, that's one of a lot of rectangles that represent this area. And in fact, how many rectangles represent that area? Infinite. An infinite. If there's an infinite number of representative rectangles in this shaded region, how wide is each rectangle?
Infinitely small.
Infinitely small. And so we need a way to represent that. Any guesses?
Don't draw a line and say it's there.
Okay, that's one possibility. Or we could just call it dx.
Oh.
Okay, this is where the idea of the differentials come into play. What does the dx mean? The dx means that it's so skinny that it's not really there. Okay, it has no thickness. Well, if it has no thickness, then how does this give you an area? But again, we're dealing with that infinite concept. So small it has no thickness, but if I put an infinite number of them together, I get an area. Okay. In other words, if I put another one right next to it and another one right next to it, and I keep doing this an infinite number of times, eventually I will end up filling in the whole area. Okay. But that's crucial for us.
So what's represented by the dx? That just
The width of the rectangle.
Oh, okay. Just the width.
Yep. And we need two things for the area of a rectangle. We need the height, we need the width. We have the height. That's where the top minus bottom comes into play. And now to represent the width, we're just going to use that dx. And you'll start to see as we build these integrals how all these puzzle pieces fit together. So from day one, I've been telling you how important that dx term or that dy term is. Now it actually has a practical meaning in there, other than what we talked about already, where it just represents the variable and all that other gunk. Now it has a physical representation. It's the width of that representative rectangle. Okay, you good so far? Every single problem when you draw a graph, I need to see a representative rectangle. It doesn't matter where you put it, as long as it's on the graph somewhere. Okay, so let's see this in motion now. Two functions, still red and blue, but now you actually have the equations. The red one is the square root of x. The blue one is x squared. So we'll start with something simple. This one's a little different because I'm not giving you vertical lines to bound the region. I'm just saying the region bounded by the two graphs. Because the graphs intercept, they give you this leaf-shaped, cat's eye-shaped thingamajobber. So we're going to find the area of that thing. I need to start with a representative rectangle. You can put it wherever you want. I'm going to put it right there for no particular reason. If you can find the area of that rectangle, the rest of this falls into place and it's not that bad. So we'll start with the easy question. How wide is that rectangle? Dx. So the area of that rectangle is dx times, how tall is that rectangle? This is where the top minus bottom comes into play. Which function's on top?
G of x.
There's no g of x up there, is there?
Yeah, that's.
Oh, there is. Oh, it's in the instructions. G of x is on top. F of x is on the bottom. That's really important. So before I move on, I want to make sure everybody gets that. Do you see what I just did? Yes or no?
What does the DFX stand for again?
D of x is the width of that rectangle. So area of a rectangle, length times width. So the width is dx. It's really, really tiny. The height is top minus bottom. Top function is square root of x. Bottom function is x squared subtracted 2. We're good to go.
How do you know the width is tiny?
Because we're making it tiny. Because all of our representative rectangles are going to be really, really skinny. And then we're going to add up all those infinite number of rectangles. Okay, let me finish the problem and then we'll see if all the pieces fit together for you, and if they don't, I'll go back and go over it. This is the hard part. If you can find the area of the rectangle, you're good to go, because this area then is just the accumulation of all those rectangles. How do I accumulate things? Integral. Integral. So the area is equal to. This is very important, don't get sloppy. List what you're looking for, because we're starting with area, but eventually we're going to be doing volume. And then you'll be combining area and volume, so you have to denote what you're looking for. Sometimes in the problem, it will give you the points of intersection. Sometimes you have to solve for them. This one I gave them to you. They intersect at the origin, and they intersect at 1, 1. So therefore, we're going to accumulate all the rectangles from 0 all the way over to 1. So we're going to add up all the rectangles from 0 to 1. How many rectangles will we have? Infinite. And what's the area of one of those rectangles? Then we use this function, square root of x minus x squared dx. Questions? Is it clear? Question?
Do you have to do the area of a rectangle, or can you just memorize that it's G minus X?
You gotta do the rectangle. You could just memorize, but when we get to the volume, you're gonna get blown out of the
Okay.
water. So if you get the idea of the representative rectangle under control here, the stuff we're doing in the future will be a lot easier. Yeah.
How do you, well, so I know that 0, 0 is gonna be the point where they intersect, but, so if you have to test for it, and it comes like,
What do you need test for it?
well, when you set up a system and see where they intersect.
Oh, yeah.
If you don't do that and say that you just had the graph and there's just like a little region, like hole missing there, then it's not continuous and it's not bounded, so you can't find it, right?
Correct. You can only find the area of a bounded region, otherwise the answer is infinity.
Infinity, okay.
I'm not gonna solve that integral, we're good with that, right? You can FN int that, you can solve it by hand, it's entirely up to you. Ballpark on how big that the answer would be?
Like 2 or 3.
Well, can we do it, how big are each of these squares?
0.25 by 0.25.
Yeah. And I've got one whole, about 2 whole. These make up a third. All right, get out your calculators. Do that. FN int that and tell me what you get. Questions?
So is there a reason that black line is there? Or
Yeah,
like-
that's the representative rectangle. That's
So it's supposed
showing.
to be, that's like, that black line is supposed to be like a really tiny rectangle.
Yeah, it could, and you can put it anywhere in that region you want to.
Okay,
You can slide it left and right.
and so DX is like,
You got it.
alright,
Sam, get out your calculator. Who's talking?
It's like 0.33.
Can somebody confirm?
Yeah.
0.33333?
Yeah,
So 1/3?
pretty much. Yeah.
Okay, so we'll go with 3 decimal places here, 0.333. And if you did it by hand, if you took the antiderivative of x to the 1/2 and the antiderivative of x squared, and plug it in, you'd probably get 1/3. But for now, that's good enough. We could also we could approximate the area by counting up the number of squares, multiplying it by 0.25 times 0.25, and going from there. But again, easy peasy. Solving the integral for me is not the major concern right now. My major concern is that you're able to set them up. Yes?
Well, we always have a picture.
Not always. No, sometimes you have to draw your own picture.
How do you know it's from 0 to 1 then? Okay.
Because that's where the two functions intersect.
So do you have to set them equal to have them?
How could we make it more interesting?
Trig.
We could use trig. Doesn't make it much more. Inverse trig? Wow. Sorry, I threw up a little bit in my mouth. You really want to go down that?
Yeah, I don't want to.
No, I don't want to either.
Rates.
All right, let's see what else we can do. Yeah, oh, yeah, 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 okay, did that, yeah. Oh, look, I did all the work already.
Do it on a polar graph.
Ooh, this could be interesting. Okay, so suppose the top and bottom change, like this guy. So we'll practice for a second. I have a picture, which I'll show you in a second, but on your notes there, just sketch what that looks like. Because you'll have some problems where you'll have to sketch the region. Doesn't have to be perfect, but it should be close enough that it represents what you're trying to solve for here. After you get it sketched, draw in your representative rectangle. And you'll see we will have a little bit of a problem here. If you're not sure, graph it on your calculator. Put the 3 functions into y equals, graph it and see what it looks like. Is that window open, Ken? Where do I hear that noise coming from?
I think it is.
That's fine, I don't care if it's open, it's an area.
This year, I did some interesting reading on Leibniz versus Newton on the plane ride back too. That was a hoot.
Oh, did they have that in like the United magazine or?
No, it was a book that my dad was reading about the Royal Society.
Nice.
Leibniz never experimented on anything, so he didn't like prove any of this. He just knew it.
Freak show.
It's kind of nuts. I think I have a problem.
Okay, we good? Some of you are still graphing. That's okay. If you're still graphing, go ahead. Finish the graph.
It's not even a shape.
Yes, it is. It's not a pretty shape, but it's a shape. And then think later we're going to take that shape and spin it around an axis and generate some 3-dimensional figure. But we're not ready for that yet. There's a reason why I have an R1 and an R2 up there. And that reason is if you start at this point of intersection, okay, now I didn't label this point of intersection. You could trust me by realizing that it's 1, -1, -2, -3, -4, 2, or how would I find that algebraically?
System.
Yeah, find out where for discussion purposes here, the blue line, which is this guy, and the red line intersect, and then we got the green one there too. And so set x plus 6 equal to -1/2 x and solve, but you will get -4, 2. Same is true over here. If I want to know where that point of intersection is, I would set the green equal to the red and solve. You'll get 2, 8. Okay. If I start at this point of intersection and I start listing rectangles, like let's suppose I put my representative rectangle right there. Everything seems peachy keen. Red function is on top, blue function is on the bottom. All of a sudden I get to the origin and trouble happens. Now I have a different representative rectangle. The red is still on top, but now the green is on the bottom. Simple solution. You need to treat it as two different problems. One problem is going to find the area of that triangle. The other problem is going to find the area of that shaded region, or not shaded region, but that R2 region. Sí, señor.
Yeah, that's supposed to be a irresolved clock.
Oh,
I don't know what the word saying is.
I don't either. And then of course that was just a 9 degree shift. Had it figured out the other line.
Yeah.
Okay, thank you.
Sure.
That was kind of fun.
Yeah, it is good. I got a whole bunch of them. All right, you with me? Anytime the top and bottom change, top or bottom changes, you need to generate a new equation. Not a new equation, I'm sorry, a new integral. So we'll start with the R1 first. How wide is that representative rectangle? dx. How tall is it, Ella?
It is like 2.
Nope, don't count.
Uh,
Because I could have put it over here. I need a general expression for how big that rectangle is.
it would be x plus 6 minus negative 1/2 x.
Perfect. Good. Okay. Red minus blue, all of that times dx will give me that first integral. Okay, so there's R1. We're going to go from -4 to 0, my first point of intersection, to the y-axis, because that's where things change. And as Ella said, top minus bottom, red minus blue, not now.
It's about where you put the rectangle.
I understand, I'll be there in a second. Now I move on to the second region. Representative rectangle. Can put it anywhere in there. What function is on the top, Casey?
The y equals x plus, x plus 6.
Good. Which one is on the bottom?
Y equals negative 1/2 x.
No.
Oh wait, the second one?
Yeah.
Oh, the other one. The x plus x to the third.
Good. So what would the area of region 2 be?
It would
The integral
be
from what to what?
integral from 0 to 2,
Good.
and it would be in parentheses x plus 6
Good.
minus in parentheses x to the third times dx.
Perfect. Another thing for future reference. Do I do, like I saw him thinking when he went from 0 to this point, do you use the 2 or do you use the 8? You think about where you're sliding your rectangles. You're sliding your rectangles left and right, which is along the x-axis. And when you slide along the x-axis, you're going to use the x values. We'll use y values later, but we're not ready for that yet. Any questions on any part of that? Cam?
So, would you suggest not putting your rectangles at like the origin or where they switch?
No.
Don't do that? Okay.
Because there really is no rectangle there.
Yeah. 'cause
That's
it's
at one point
two
where there
different
isn't a rectangle.
functions.
Yeah. And so if you're doing this problem, what I didn't do is draw my representative rectangles. Your problem should actually look something like this. So you can see the two different rectangles there. And again, it seems silly to draw that little vertical line in there to represent the rectangle, but knowing where we're going in the future, it will make your life a lot easier if you get used to working with this representative rectangle concept. Okay? Not bad integrals to solve. You can FN int them, you can do them by hand, whatever it is. You can simplify the function first, whatever's easiest. Okay, but we're going to find those areas. This is another thing that causes some problems for people. There's no such thing as negative area now that we're doing this. We're finding a positive area of these regions. So if it goes below the x-axis, you're okay. Okay, again, problems. Can you do this on your own? Well, we'll find out. Again, FN int is probably the easiest way. I'm not so concerned. By now you should have a pretty firm grasp on doing basic definite integrals. The idea here is, can you set it up? We're gonna stop there for today. Okay. Now, what are we gonna do in the future? Well, you'll notice that every one of my representative rectangles were vertical, where its width was dx. Well, first thing we're gonna do tomorrow is turn those rectangles sideways and deal with horizontal rectangles where everything will be in terms of y. Why would I bother doing that? I'll show you some examples. Once we get that under control, then we're going to start taking all those bizarre figures and spinning them around axes. Sometimes it'll go around the x-axis, sometimes it'll go around the y-axis, sometimes it'll go around some random line. Sometimes it'll be touching the line, sometimes it won't. So in other words, sometimes your figure will have a hole in it, sometimes it won't. So you can think about something like this. So we did this already, right? If I spin that around the x-axis, we already talked about we'd get a cylinder, right? This becomes a circle, and you get your cylinder there. What happens what's it look like if I take that same rectangle and move it up off the x-axis? And spin that around the x-axis. Now what do you get?
Coffee mug. Donuts.
Nope.
Bagel.
Nope. Cylinder with a hole in it.
That's
Right.
a bagel.
It's not a bagel. How do you get a bagel?
Take a
A
cylinder.
bagel, by the way. Go ahead, Pat. What'd you say?
I was gonna say, like, you take a cylinder and you stretch it all the way around.
Like
I
a
don't know.
slinky. You know when you take like a slinky and you go like this?
Perfect. If I take that circle and revolve it around the x-axis, I will get a donut or a bagel. Also known as a torus, by the way, in fancy mathematical speak there. So we'll be figuring out all of these different figures. Your job is not going to be to draw them, it's going to be to calculate the volume of those things, but that comes in the future.